Hello and welcome to another lecture for my class, PSYC 440-640, the class that's called Experimental Methods, but is really more of a data analysis class that is appropriate for basic experimental and non-experimental studies. And as is usual, I'm beginning with a webcomic, this one from the excellent webcomic series xkcd.com, hopefully putting us in a little bit of a statistics, or at least graphing frame of mind to get us ready for the lecture. And buckle up, because this is a big lecture. It's one of those ones that I've edited again and again over the months and years, and it seems like I keep on adding stuff, and I know that can be maybe a little bit frustrating to students, but I hope, or I think what I've added is mostly very interesting and useful stuff. So if you're patient, bear with me. I think you'll learn quite a bit from this lecture. Take some breaks if you have to. I'm actually about to make myself a very strong cup of tea to keep awake and keep focused during this lecture. So if you need to do that too, by all means go ahead. Anyway, the name of the lecture is More About Models, Parameters, and Errors, which I think has a nice ring to it. And by way of an overview, what we're going to do today is just quickly run through a little example. Now, if you're watching this video on YouTube, you won't be able to play along with the data set. Well, actually, I suppose you could. You could just copy it from the screen. If not, if you're in my class, you have access to this data set on our Blackboard site. Then I'll talk a little bit about degrees of freedom, a complicated and sometimes I think misunderstood topic in statistics. I'll do a little bit of a review. Then I'll start talking about sampling distributions and try and make a connection between sampling distributions for test statistics and hypothesis testing. Okay, so here's the part to just practice or try something that we did last time. Imagine that you're a health psychologist who's studying stress. So in your laboratory, you're doing some sort of experimental study that involves a stress manipulation. Perhaps people who come into the laboratory are assigned to either just wait quietly or to wait with the expectation that they'll have to give an embarrassing speech to a group of people, so they're in a stressful state, relatively speaking. That's your independent or predictor variable is whether or not the person is in the manipulation group, and the dependent or outcome variable is heart rate change, so how much their heart rate changes from a baseline before they're given instructions to some period of time after they've sat there in knowledge of their instructions. So maybe like change in beats per minute is your variable. So here is some data. I have 10 participants and I've made up some fake data for their change in heart rate in beats per minute, and I'd like you to calculate the mean, median, and mode, our estimators of central tendency, and also the variance and standard deviation, our estimators of sort of shape, and also, of dispersion, and also skew and kurtosis, which are our estimators of shape of distribution. And again, I suppose if you're just watching this video on YouTube, you can easily copy these numbers into a spreadsheet like Excel and do this, I hope, or I think, pretty quickly. All right, assuming that you're ready to go on, here are some answers for you. Mean, median, fairly well lined up. Mode, there isn't one because there's not one single most frequently occurring value. Variance and standard deviation, quite a bit of dispersion in this data set. A little bit of negative skew and a somewhat kurtotic distribution. Also interesting to note, we have a potential outlier here, someone whose heart rate change was 0. Now, it's not for sure that this person is there's something unusual going on with this person. It may be that they're just a rather calm or unreactive person. But if I was looking at this and this was real data, I might start to wonder if this person perhaps made some sort of mistake, if they weren't paying attention, or if my lab experiment folks made some sort of a mistake, if our equipment wasn't working properly, or so on. It's even possible that this person maybe doesn't belong in our sample to begin with, because he or she comes from some sort of different population, someone who's had training in speaking in public. So for them, speaking in public is not very stressful. And assuming we imagine that puts them in a different population, maybe they shouldn't be in our sample anyway. So a general point I made last time, I think, or if not that, the time before, is that part of the interest or part of the reason for doing so-called descriptive statistics like this is to kind of get to know the data in your sample and start to look for potential problems, particularly things like outliers, and start to figure whether or not this sample of data will provide you with robust, non-biased estimators of interesting population parameters. So with that little bit of practice out of the way, where did we leave off last time? Well, last time I kind of generally introduced the idea of models, and about where we left off I was talking about error. And error is defined using our kind of generic equation as the amount that a prediction made by a model misses the observed values of the model. So if we rearrange the equation data equals model plus error, we can get quite easily error equals data minus model. So the discrepancy, just simply put, between what the data in our sample actually are and what the model predicts those values should be. So an example of an error estimation would be something like the variance, which is just the mean squared error for a model where that model is just the mean of a sample of data. So one of the things we think about when evaluating models is error, and that'll come up a lot in this lecture and the next lecture and certainly throughout the rest of the semester. Another thing we think about when evaluating models is their complexity, especially their relative complexity if we have two or more models that we're comparing to one another. Now, complexity has to do with things like the size of the sample, the number of elements, or more specifically put, the number of parameter estimates in a model, and this kind of mysterious idea of degrees of freedom. And that's what I want to get to right now. So degrees of freedom. Kind of hard to come up with a good graphic for a slide on degrees of freedom, but when I started looking through some of the sources that I typically go to, the word freedom kept on showing up or returning to me pictures of distant horizons and open vistas, and so I suppose that's what we got here. Degrees of freedom, the vanishing highway in front of us. So what are degrees of freedom? Well, no one knows. That's actually not true. That's just something a statistics teacher in graduate school once jokingly told me. What they are is an elusive concept that occurs throughout statistics, and this definition, if you want to call it that, comes from nothing less than the Cambridge Dictionary of Statistics, 2nd edition. I'm putting both these up here, of course, to have a little bit of fun with the whole idea of degrees of freedom, but to also highlight that they are this kind of tricky concept that almost any student who's had any experience with statistics is sort of familiar with. Like, yeah, I've heard that phrase before, but which many students, and many professors for that matter, might struggle to define or describe. To my mind, there are sort of two ways to think about degrees of freedom. One way is algebraically, and the other way is geometrically. Now, either way you think about degrees of freedom, there are really two important issues. The first is the number of observations that we're dealing with. That's our data. And the second is the complexity of the model that we're applying to that data. So here we are again with those ideas, data and model, from our generic equation, which we keep going back to. Those two ideas or issues are important for thinking about degrees of freedom, whether you choose a more algebraic way of looking at degrees of freedom or a more geometric way of looking at degrees of freedom. And just to try and make this more obvious, or try and explain it in a different way, we're thinking about the number of pieces of information that we need to explain. That is, the number of observations for our outcome variable, or put yet another way, the data we have. And we're thinking about the complexity of the explanation that we're making, the number of necessary relationships between the data that exist in our model. In some ways, this takes me back to that idea of finding a balance. When we're building a model, or when we're comparing two models in statistics, it seems like we're always trying to strike a balance between parsimony and explanatory power. In general, adding additional elements to a model, whether they're constants or parameter estimates, whatever, tends to increase the explanatory power of that model. So in past lectures I've used the example of trying to predict people's level of depression based on their level of alcohol use, or you can make a more complicated model that uses not just alcohol use, but in addition a level of neuroticism, a personality trait associated with depression, or maybe another model which has 3 predictors in it, 3 parameter estimates. So alcohol use, level of neuroticism and recent life stresses and so on. Each of those models, as we're adding elements to it, becomes potentially better at explaining variance or variability in our outcome variable, explaining the data, but it also becomes more complex. And there's kind of this trade-off. It's good to have a powerful explanation for the data, for whatever phenomena you're interested in studying, but not if it comes at a great cost of complexity, such that the model becomes kind of unwieldy or difficult to understand. And degrees of freedom, to tie it back, is this way of kind of balancing or considering both data and model, explanatory power and parsimony. Now, a couple slides back, I used the term necessary relationships, and that's deliberate because in many stats textbooks, when you look up degrees of freedom, you'll see an equation that looks something like this. Degrees of freedom equals n, sample size, minus r, number of relationships. What does that mean? Well, the example that is given in many stats textbooks is something like this. Imagine you had a group of people on a sports team and you're trying to put them in some sort of order, like order in terms of who gets picked to play in a particular game or something like that. Now, I'm not much of a sports person, to be perfectly honest, so I'll pick a slightly different variant of this. Imagine you had a group of people, let's say the Beatles, and you wanted to put them in some sort of ranking from first position of importance to last position of importance. Well, the first position you might put John in because you figure, well, he's kind of the coolest Beatle and he's got the most kind of interesting songs. Now, he could in principle go in any place because all four positions, first, second, third, and fourth, are open to him. We might go ahead and put him in first spot. The second person we pick, of course, would be Paul because he wrote all the other really good songs. Well, that's probably not true, but many of the other really good songs. He now can go in any of three remaining places. Let's say we put John in first. There are now three remaining spots for Paul to go into. I was always kind of a fan of George Harrison's writing, so I wouldn't necessarily pick him third, but let's say you did. You could only really put him in two remaining spots, or one of two remaining spots, the third or the fourth position. And then poor old Ringo, who's really a much better drummer than I think he's given credit for, has only one position left to go in. So what you have, again, is four people, and you're trying to put them in some sort of a ranked order. To put this another way, you have four pieces of information that you're trying to explain, four observations for participants, for Beatles, and you have one way of explaining the information. And by explaining, I mean here, there's one relationship you're trying to develop or kind of use in terms of explaining their position, and that is relative order or rank. So degrees of freedom equals n minus r. 4 Beatles minus 1 relationship, that is rank order, equals 3 degrees of freedom for this model in this data. Now, an important idea here is that we have 3 degrees of freedom for the model in this data. However, if we changed the model, in some way made it more complex than just simple rank ordering, or if we changed the sample size, if we had more or less data, that calculation of degrees of freedom would necessarily change. And so again, the important idea, or the point I'm trying to make, is that degrees of freedom are necessarily describing a relationship between model and data. They don't exist in splendid isolation. They exist with reference to this kind of relationship that exists between data and model. Now, is this example helpful? Again, it's an example you often encounter in statistics textbooks, that is, ranking some group of people like members on a sports team, or in my example, Beatles. Maybe it's not that interesting or not that helpful. We don't often make ordinal calculations in research in psychology, at least not the type of research that I do or I'm most familiar with. Maybe there are some exceptions to that, like if you work in educational or school psychology, you might use class ranking or some sort of similar ordinal way of organizing data. But again, the important idea here is that I'm trying to emphasize this idea of a necessary relationship, how the data is connected or explained or predicted by the model. And if my example isn't really all that helpful to you or doesn't connect to research you do, let's think about it a different way, and let's use a more familiar calculation. Let's use the mean instead of rank order. And this is more common, I think, in psychological research, especially in experimental designs where we have different groups, because we might be comparing the mean level of alcohol consumption in one group as compared to another group, or the mean level of reaction time in one condition as compared to another condition. This is probably a bit more familiar, and fundamentally the basic idea still applies here. And the reason why it still applies is that the mean is just a simple model. It uses sample data to represent population data, or we could sort of equivalently say that the mean is a parameter estimate. It's estimating specifically the population mean. Now, when we calculate the mean for a sample of data, of course, all the data are free to vary. As you add up the different pieces of data in your sample, you don't have to restrict the values that any of them have, or sort of put them into particular positions or add them in particular orders. Each of them are just free to vary as they will. So just add up all the values together, divide by the total number, and bam, you've got the sample mean, as we all know. Now, in order to evaluate the error for the model, that is the mean, we can go ahead and calculate its mean squared error, aka its variance. Now, when we make this calculation, in a sense, not all the data that go into the calculation are free to vary, because they have a certain relationship to each other in that calculation. Specifically, we're comparing each value to the mean, and in this sense, they are all linked together. Now, if we look at the familiar formula for the standard deviation, which is just the positive square root of the variance, we can see that idea of the data being linked together kind of reflected in two places. In the numerator, you can see that each data point, x sub I, is compared via subtraction to the mean of the sample. And in the denominator, you can see that rather than dividing by n, as we did in the calculation of the mean, we're dividing by n minus 1. And we're doing that, in a sense, to adjust for that complexity, or adjust for that relationship that exists between the data when we're calculating its error. And as an interesting side point, I'll note here that in Excel, you can calculate standard deviation, or for that matter variance, and actually some other different functions, for a sample, that is, treating the data in your data set as a sample of a larger population, in which case the calculation is done with the n-1 denominator. Or you can calculate standard deviation for the population, which is treating the data in your data set as the entire population of values. And if that's the case, then you get the n denominator, not n-1. Now, to be clear, in psychology, we pretty much always use samples from population. So we're almost always dividing by n-1, if you will. I really struggled to think of situations in which you have the entire population of cases for your data set. I don't know, maybe if you're studying giant pandas, you literally can have all the pandas that exist at one time in your data set. But outside of that weird example, and why are you studying pandas in psychology anyway? I don't know. Outside of that weird example, you're almost always treating your data in your sample as just that, a set of values which are drawn from a larger population, which is much, much bigger, and which we're trying to estimate in some way, as we've discussed in past lectures. The important idea here is that when we evaluate a model, we often consider error, which is just the opposite of explanatory power, and complexity. And degrees of freedom are this way of kind of considering error and complexity, or explanatory power and parsimony. One way to think about this is using degrees of freedom, and we can think about degrees of freedom algebraically using this kind of generic formula: degrees of freedom equals n minus r, or degrees of freedom equals amount of data we're trying to explain minus complexity of the explanation, if you want to think about it in a more conceptual way. And just for an example, I used standard deviation here to kind of highlight that. Now, if you're like me, thinking about degrees of freedom algebraically kind of makes a little bit of sense, but it's a little bit hard to wrap your mind around. I find it a little bit easier to think about degrees of freedom in terms of geometry. And here what we're doing is we're focusing on the elements of a model, particularly the parameter estimates, which are the components of most models and which define those models in geometric space. And if that seems a little bit heady and kind of mind expanding, hold on, because I'll show you some pictures that hopefully will make it seem a little bit more obvious. Now, if you're in my class, especially if you attended the lecture where I ran through these slides, you've already done this example. If you're not in my class, well, you can follow along by looking at my SPSS data frame in the background there and copying those values into SPSS or some similar statistics package, or just follow along and pay attention to what I'm saying. In SPSS, as most of you probably know, you can do some fairly good graphing. There are some real limitations, but the graphing that you can do in SPSS is useful for illustrating the geometry of some fairly simple types of models. So right up front here, we have our data set that I've made up for this class. It's just some kind of made up data for an outcome variable y and two predictor variables x1 and x2. So the first thing I'm going to do is I'm going to open up the work tool for simple scatter plot. I'm going to put the outcome variable y, appropriately enough, on the y-axis. Then I'm going to put participant ID number on the x-axis, which admittedly is a little bit weird. This is something that I did in this data set just to kind of spread out the data, even though you probably would never do this in real life. You would just, you would not use participant ID as a predictor variable, or for that matter as an outcome variable. I'm just doing it to help me visualize the data a little bit better. And the reason why I'm doing that is I want to make a very simple model where I'm predicting y based on just the sample mean for that variable. So this model is very simple in the sense that it has one parameter estimate. It uses the sample mean for the outcome variable to predict the population mean for that variable, whatever it happens to be. So using SPSS's scatter plot tool, I probably get an output figure that looks a little bit like this, where I have my outcome variable on the y-axis. On the x-axis, I have participant ID, just to kind of spread out the data and give it that kind of familiar cloud of dots appearance. Now the line passing through those dots is my model, and that model is defined by one parameter, its intercept. This model has no slope. It just intersects the y-axis at a particular point that's defined by the mean of the outcome variable y. Now, sample to sample, this mean would be a little bit different. If I drew a different sample from the population, the mean might be a little bit higher. If I drew yet another sample from the population, the mean might be a little bit lower. So in a sense, this model can move in one direction in space. The flat line can slide up the y-axis, or it can slide down the y-axis. So I think you can maybe intuitively understand this model has, in a sense, one degree of freedom to move around in space. It can kind of move in one dimension of space. If I wanted to write out the model, I might write it something like this: predicted value of y equals this intercept, whatever it happens to be. So you can see hopefully that this one degree of freedom to move in space corresponds to one parameter estimate in our model. Now let's go back to the scatter plot work area, and now we're going to do probably what's a little bit more familiar to you if you've ever taken a class on regression. We're going to make a basic scatter plot where the outcome variable y stays on the y-axis, but one of the predictor variables, let's say x1, goes on the x-axis. And the reason why I want to do this is I want to make a simple model where I'm predicting level at the outcome variable from a predictor variable. I'm predicting y from x1. Now, this model is going to have two elements in it. It's going to have a slope and an intercept, or equivalently put, it's going to have two parameter estimates, b sub 0 and b sub 1. And if I hit the continue button or the OK button, I'll get some sort of output that looks a little bit like this. So again, the cloud of dots is the familiar scatter plot for y and x sub 1. And the line is just that. It's a line. It's our model that tries to explain or describe the outcome variable in terms of the predictor variable. And the model is also a line like it was before, but now it's defined by two parameters. It's got an intercept and a slope. And again, if I that intercept and slope are going to be particular values for this sample of data. But if I drew another sample from the population and did essentially the same process of making a scatter plot and drawing a line, I'd probably end up with a line with a slightly different slope and a slightly different intercept. And if I drew yet another sample and repeated the process, I would again have a slightly different slope and a slightly different intercept. So in a sense, this line that is my model can move in two directions. It can move in one direction, kind of sliding up and down the y-axis, having a greater or a lesser intercept. It can also rotate in the sense of having a greater or lesser slope. So again, if you think about this like kind of an object in space, it now has two kind of degrees of freedom for its movement through space. That line can slide up, it can slide down, it can tilt forward, it can tilt backwards. And if we wrote out this equation for the model, we'd write something like this. The predicted value of y is going to be b sub 0 plus b sub 1 times x sub 1. So that model now has two parameter estimates in it, a slope and an intercept. Two parameter estimates, two kind of ways of moving in space. We're thinking about degrees of freedom in a somewhat more geometric way. Let's do another one. Let's go back to the SPSS chart builder and get rid of simple scatter plot and instead drag the tool for 3D scatter plot up into the work area. Now 3D graphing in SPSS is pretty crummy. I've been looking around for better software to do better graphing, but for the sake of this example, this is all I've got. And if you have access to SPSS, this is probably all you've got. And that's okay, because it's enough for us to make a more complicated model where again, we're still predicting the outcome variable y, but now we're using two predictor variables. We're using x sub 1 and x sub 2. And you can see them kind of arranged in the workspace a little bit like this, with x sub 1 on the x-axis and x sub 2 on what's sometimes called the z-axis, kind of descending or moving backwards into the plane. Anyway, the model that we're going to make will actually have three parameters in it. Or if we're thinking in terms of the sample data, it'll have three parameters, estimates for those population parameters. It'll have b sub 0, b sub 1, and b sub 2. So once I've arranged these variables this way, I go ahead and hit the OK button. So once you hit OK, SPSS will give you some sort of output that looks a little bit like this, some cloud of dots or representation of a cloud of dots in three-dimensional space. And what's really interesting here is that the model for this data is not a line anymore, rather it's a plane. It's a plane that sort of slices through that cloud of dots like a sword, or kind of like a sheet of metal that passes through a cloud of dots. And of course, for this particular data set, that plane is going to be defined by three parameters: an intercept and two slopes. An intercept being where the plane kind of slices across the y-axis, and a slope referring to the angle or sort of the pitch on the axis for x1, and another slope for the angle or pitch on the axis for x2. And within our one sample of data, those values, intercept and slope and other slope, are going to be whatever they are for our data. But of course, if we gathered a new sample of data from the same population, we'd expect those three values to be slightly different. If we drew yet another sample of data, they'd be different again, and so on, just like with the previous examples. And thinking about it this way, hopefully you can imagine or sort of visualize in your mind that the model, the plane, can move in one direction up and down, but it can also kind of rotate in two other directions. It can slide up and down, having a greater or lesser y-intercept, and it can pitch, having a greater or lesser slope on the variable x1 and a greater or lesser slope for the variable x2. So it has, in a sense, three kind of ways of moving in geometrical space. And if we write out the model, algebraically, we can see it would be something like this. Y sub, the predicted value for y is equal to this intercept plus the slope for the first predictor variable and the slope for the second predictor variable. So we'd have three parameter estimates, one intercept and two slopes. Now, once we get much above 3 dimensions, that is 2 predictor variables, it becomes very hard to visualize what any of these models would look like. They become sort of hypergeometrical shapes that I can't easily visualize or imagine. But the principle is the same, whether we're talking about a model with 1 predictor variable in it, 2, or 10. We're always relating the number of observations we have, that is to say the data that needs to be explained, and the model complexity, the parameter estimates used to explain that data. So again, the important idea when we consider a model is when we evaluate a model is we consider its explanatory power and its complexity. And again, just like when we thought in a more algebraic way, the degrees of freedom are this way of relating these two ideas. And we can do that algebraically, and we can also do that geometrically. So an interesting idea to reflect on is that necessary relationships, this concept I introduced when we thought of degrees of freedom in a more algebraic way, are the same as parameter estimates, which is this concept I introduced when we thought of degrees of freedom in a more geometric sense. If you write out a model, like the one I've written out here, this one has elements like a slope, an intercept, and a slope for the first predictor variable, and a slope for the second predictor variable. Each of these elements is a relationship that links the data together, and each of them is an estimate of a parameter. So either way, we're kind of thinking about the same thing. It probably goes down to just whether you are more comfortable thinking in an algebraic frame or a geometric frame. As I noted earlier, for me, degrees of freedom as a concept really clicked once I got the geometry idea, and that made a lot of sense to me, and perhaps it will to you. But really find something that you feel comfortable with and hold on to that central connection of relating data to complexity of model. That's really the point of degrees of freedom. With that in mind, let's do a little bit of practice. Imagine that you're a clinical psychologist who's studying marijuana use and you're interested in the relationship between marijuana use and anxiety. Imagine you have a pretty simple type of study where you're looking at a predictor variable, which is level of marijuana use, which you're operationalizing as something like reported days of use in the previous month, which I guess can range from like 0 to 30 or 31. And your outcome variable is anxiety, which you're measuring on the trait version of the state trait anxiety inventory, which is a fairly well used and well liked measure of just kind of overall relatively stable level of anxiety. And so you have 20 people in your study, you contacted them somehow, and you asked them to fill out a marijuana use questionnaire that includes number of days used in the previous month, and you ask them to fill out the state trait anxiety inventory. The question I have for you is, if you try to predict level of anxiety from level of marijuana use, how many degrees of freedom will your model have in this data set? Think about this for just a moment, or if necessary, or if you think it'll be helpful, try and sketch out what the scatter plot relating these two variables might look like, or think about how you would go about analyzing the data to answer, to look at the relationship between these two variables. Now, I made up this data in Excel, and I made it up to look like this. You can see days of marijuana use in the previous month on the x-axis, anxiety on the y-axis. Again, this is just data I made up, but you can imagine pretty easily making a simple regression to predict the one variable from the other. That regression would be a model that would have that could be expressed geometrically as this line, that it's not a flat line, it's a line with both an intercept and a slope. So let's think about this. We have data, we have 20 pieces of information. We have model. The model has two parameter estimates, or two kind of features of geometric features. It's got a slope and an intercept. So degrees of freedom is 20 minus 2 equals 18. Okay, if you made it so far, good for you. We're a little over half an hour in, and if you haven't already done so, now would be a great time to stop for one of those strong cups of tea or cups of coffee, because what I'm going to do in the next couple slides is offer a bit of a review to kind of talk a little bit about what we've learned so far. Well, so far we've learned that models are usually made of parameters. These are data for predictor variables in the population that we estimate from data in our sample. So for instance, if we're writing out a model in terms of its parameters, we might write it using the uppercase Greek letters. It'd be kind of the same idea as writing out with lowercase letters to suggest that we're working with parameter estimates from the sample. In some cases, we have very simple models where all the data are given the same predicted value. So it might be something like just a constant value. And in other cases, we have models which are a little bit more complicated, where all data get some predicted value, which is then adjusted by a variable value. This is perhaps the more familiar simple regression, where we have both a slope and an intercept. Okay, with that out of the way, just a brief pause for a review. Let's push onwards and let's talk a little bit about sampling distributions. Now, in order to talk about sampling distributions, let's consider an example of a college counseling center. Now, if you're enrolled in my class, you have access to some data sets made of fake data for this example. And if you're not enrolled in my class, if you're just watching this video on YouTube, I'm sure you'll be able to follow along. Now imagine that this counseling center has a relatively standard form of treatment that it applies to most of the clients who come in for help. And then imagine that after a while a new form of treatment is introduced. Perhaps it's mindfulness meditation or acceptance and commitment therapy, some sort of new treatment which the folks at the counseling center are trained on. And now they have two options. They can use their standard treatment, or they can use whatever this new treatment is. Now clearly a really interesting question would be, is this new treatment better than the old one? Is it associated with better outcomes for the clients? You could imagine being a clinical psychologist who likes to study treatments, as many of us do, and setting up a fairly simple independent design experiment where you have a predictor variable, which is group, whether or not people who are clients of the counseling center get the new form of therapy or they get the old form of therapy, and have some sort of an outcome variable to measure overall functioning, overall psychological functioning. And here, an easy way to operationalize that might be the global assessment of functioning, or the GAF, a rather crude measure of just generally speaking how well or how poorly a client is doing. With this basic design in place, you could recruit a sample of people, let's say about 60, and you assign 30 people to either be in the new treatment group or in the old, kind of treatment as usual control group. To represent this pictographically, we could make a little flow chart kind of like this, and you see here participants are assigned to be in either the treatment or the control group. Let's hope that this assignment is done randomly so that we have a true experiment, because if it is, then we would expect our control group to be, hopefully, given a large sample and given random assignment, to be probabilistically comparable to our new treatment group, except for the fact that they differ in the types of treatments they're given. Put more simply, the control group is a good counterfactual if we have a large sample and random assignment. So once we've taken care of that, we allow all the people in these groups to have their respective forms of psychotherapy, and then 6 weeks or 10 weeks out, we measure their overall functioning and we look to see if there's any sort of difference. Now eventually, of course, we want to compare these two groups and address that question that I mentioned before, which is which group has better overall functioning. But let's imagine first we want to consider, or we want to ask a question, what's our overall level of functioning for people in our sample, regardless of which group they end up in? Let's say that you're curious about this. The director of the counseling center says, hey, wait, before you compare these two forms of psychotherapy, could you tell me just, in general, how ill, how sick, or how good or poor is the functioning of the folks who come to our counseling center? And let's imagine that you want to compare that level of functioning that you observe in your sample to a hypothetical value of 60 on the global assessment of functioning. And I'm calling this a hypothetical value because I'm kind of picking it out of the air. 60 is roughly the threshold between where you mark mild symptoms and more moderate symptoms of pathology on the global assessment of functioning. So for instance, if you crack open a copy of the DSM-4 TR, I don't know if the GAF is in the DSM-5, but anyway, if you look up the GAF, you can see here that roughly around 60 is you can make a dividing line between where people are having mild or very little symptom or problems, and where they're having moderate or more severe problems. Also, you can see from this image that the basic setup of the GAF is that it runs between 0 and 100, with higher values corresponding to greater levels of functioning. Now, with that in mind, you could go ahead and recruit a sample of people and apply the treatments and follow them over time, and then you could compute an overall sample mean global assessment of functioning. If you're enrolled in my class and you have access to the data set, I encourage you to go ahead and do this just for practice, but if not, you can just pretend as if you did and follow along. Now, it turns out that the sample mean is not 60, it's actually a little bit bigger. I think it's like 68.23. Now, what if we guess, though, that the population mean is 60? That is, what if we imagine that in the entire population of people who go to college counseling centers, the mean level on the GAF is 60? If that sample, or if that's the case, then is the sample mean that we've observed significantly different? Or put another way, would it be pretty rare or uncommon to draw a sample with a mean level of 68.23 from a population where the population mean is actually 60? Well, we've got one sample of people from that population. We've computed one sample mean. We could go ahead and do that again. We could gather a new sample of 60 people, assuming we had the time and resources, and we could put them into treatment, and we could measure their global assessment of functioning. And we could actually do this again and again, each time computing a mean. If we did this a very large number of times, technically an infinite number of times, we could create a really large distribution of values for sample means, each of which is an estimator of the population mean. So repeated sampling from a population. Again, each time we'd expect the sample mean to be slightly different. The first time it was 68.23, the second time it's 54.78, and so on and so on. Each time that sample mean, which again is estimating the population mean, is slightly different. Technically, this is called sampling variation, or sometimes sampling error. Recall in the previous lecture I talked about how variation and error are sometimes used as words interchangeably. The point is, by going through this process, if we had the time and resources to do it, we could eventually construct a sampling distribution, which is just a distribution of values for an estimator, aka a statistic. In this case, that statistic is just the sample mean, drawn from a very large number of samples. So you could imagine you've spent years and years of your life repeatedly running this one very simple experiment, just time after time, semester after semester, gathering 60 people, running them through treatment, measuring their GAF, and after all that work and effort, you have created not an infinitely large data set, but a pretty large data set of values of the means from all those different samples. If you plotted those as a histogram, or if you set them up as a table, you could pretty easily compute the standard error, which is just the standard deviation of a sampling distribution for a particular statistic. Now, in the case of this example, what you would compute is the standard error of the mean, which is, again, just the standard deviation of a distribution of means. If you're having trouble picturing this in your mind, here's just a nice pictographic representation. We have 3 samples here. Each sample, we're assuming they're all drawn from the same population. Each sample has its own distribution of values, and from that distribution of values on whatever it is we're measuring, we compute a statistic, let's say an average. So you do it for sample 1, do it for sample 2, do it for sample 3, and so on and so on and so on. And you take all of those statistics, all of those averages, and you put them into their own distribution, a sampling distribution. And again, technically a sampling distribution is just a distribution of test statistics across an infinite number of samples. Now, sampling distributions have interesting features, and one of them is that if the samples that were used to create those sampling distributions are themselves individually large. Now, large is a vague term, but in the world of psychology and the behavioral sciences, we typically think of a large sample as being, greater than 30 participants or 30 observations. If those samples are large, then the sampling distribution will have a normal shape. And this is something that can be demonstrated by simulation, or it can be proven mathematically by mathematical statisticians who do some really high-level work that is a bit beyond me. But anyway, just trust me on this. A sampling distribution will look normal. Also, the mean of that sampling distribution will be an unbiased estimator of the population mean. Also, the standard deviation of that sampling distribution, aka the standard error of the mean, will be approximately equal to the standard deviation of the sample that you drew divided by the square root of the sample size. And this is going to be really useful to us as a calculation because, as you could well imagine, it is in principle possible to create a sampling distribution by repeatedly sampling a population over a very long amount of time and just generating it yourself, but in practice this is something that we would rarely have the time or resources to do. So instead, what we want to do is make some assumptions about the nature of this sampling distribution, including the assumption that given a large enough sample size, we can compute the standard error of the mean by using the standard deviation of the sample that we have. If that seems a bit vague or a bit confusing, hold on because I'll get more to it later. But first I want to focus on that claim that I made that when sample sizes are large, the sampling distribution for a test statistic drawn from those samples will be normal in shape. Why is this? Well, the reason behind it is the central limit theorem. And the central limit theorem just proposes that if large samples are drawn from a population, then the sampling distribution of a statistic like a mean or a total score will approximate the normal distribution. And the greater the sample size, the better the approximation. Now, I've said that this can be proven mathematically, and it can also be demonstrated via simulation. And I think we can do a kind of a simple simulation right now to illustrate, I hope, how this works. Imagine that you're a health psychologist and you're studying the prevalence of a particular disease. So you might do a study that's very simple where you just survey people. You sample a population of patients in a hospital system, or students in a school system, or something like that, and you have a single outcome variable, which is just diagnosis of a disease. And to keep it really simple, let's imagine that outcome variable is dichotomous. It's a categorical variable with only two possible levels. So each individual person in your sample from whatever your population is either has the disease or doesn't have the disease. And let's just assume that you're able to measure that fairly precisely because you conduct clinical interviews with each of those folks. Now, I said we wanted to simulate this. Let's simulate this study by using coin flips. So imagine just flipping a coin, or don't imagine it, even just do it yourself right now. We're going to use coin flips to represent each participant in the study. So if we flip a coin for one participant, and if it comes up heads, then we imagine that participant actually has the diagnosis that we're interested in. And if it comes up tails, the person doesn't have the diagnosis for that disorder. If we do that, then we can create a total score for each sample, and the total score will just be the number of heads, which will be, of course, the prevalence of the disease. So imagine you have a sample of 4 participants or 4 people. You flip a coin 4 times, you add up the number of heads, and the number of heads is just the prevalence of the disease in that sample. Again, we're kind of operationalizing this as the diagnosis of a disease. So again, let's simulate a very small sample of just n equals 4. We're going to flip the coin 4 times. We're going to add up the number of heads and record this total score. This is the prevalence of the disease in our little sample of 4 people. Okay, now simulate another sample of sample size n equals 4. So flip the coin 4 more times. Add up the number of heads, record that total score, and that's the prevalence of the disease in your new sample. do it again. And as you do this repeatedly, flipping the coin 4 times in a row, recording the number of heads, start making a frequency table for all the total scores that you get. How many times does a total score of 1 heads out of 4 come up? How many times does a total score of 3 heads out of 4 come up? And so on and so on and so on. What you're doing is you're making a frequency table, you're making a sampling distribution for a test statistic, in this case it's just total number of heads, for a large set of n equals 4 samples. So we keep doing this, and we make a histogram for the sampling distribution, which is we just represent that frequency table pictographically. What's that shape, or what's the shape of that distribution going to look like? Well, you could do this by hand, literally flipping a coin with your hands, or there's easy software that will do this for you. Here is a simulation of a very large number. I think it's something like 500 or maybe even more than that runs of 4 coin flips in a row. And you can see that this sampling distribution has something of the kind of familiar bell-shaped curve, at least a little bit. Clearly the value that shows up the most frequently is the 2 out of 4 participants are flipped as heads. So why is it the case that 2 heads out of 4 flips occurs the most frequently when we do a very large number of samples and make a sampling distribution? Well, if you think about this for just a second, it'll probably make sense to you. Consider the outcome 0 heads out of 4 flips. That can only occur one way in a run of 4 flips. Literally, all the flips have to come up not heads or tails. Likewise, the outcome of 4 heads can only occur one way. Out of 4 flips, every single one has to come up heads. So if you think about it that way, or if you look at my little table, you can see that some outcomes, 0 heads, 4 heads, can only occur one way in any one set of 4 flips. Likewise, or moving on, 1 head or 3 heads, those can occur 4 different ways out of a run of 4 flips, and 2 heads can occur the most different ways, 6 to be precise. So you can imagine if you're doing large numbers of runs of 4 flips, you're gathering or simulating large numbers of samples, then over time 0 and 4 as the outcome, the total, are going to occur just the least number of times in that long run. 1 and 3 are going to be somewhat more common, and 2 heads out of 4 flips is going to be the outcome that's just going to show up the most frequently over a very long run of repeated 4 flips. By the way, this idea of probability as frequency over a long run of samples is basically the basis for the frequentist model of probability, which is a model or a notion of probability that really a lot of our statistics, at least the kind I'm going to talk about in this class, are based on. So just to look at it again, here's our sampling distribution for sample sizes n equals 4 that we've simulated with our 4 coin flips. Let's imagine doing this again, except this time flipping the coin 8 times. Now, this starts to get a little bit cumbersome for you to do by hand, so just trust me when I show you some figures from a simulation that I did myself. Here is n equals 8 sized samples done a very, very large number of times. Again, I think this was like 500 or 1,000 or even more. And the sampling distribution looks, again, symmetrical and it has that somewhat more bell-shaped look. Do my simulation again with 16 size n equals 16 samples, so 16 coin flips, if you can imagine doing that a very, very large number of times. And the sampling distribution at this point is kind of starting to look like our familiar normal curve. Sample size gets to 32. Run that simulation a very, very large number of times. It's almost there. And if we run the simulation again with sample size n equals 64, a very, very large number of times, we get a sampling distribution that's pretty much a normal curve. So the central limit theorem tells us that large size samples are associated with sampling distributions that approximate a normal curve, and that the larger the sample sizes get, the better that approximation gets. If we want to be a little bit more technical about it, the central limit theorem is telling us that sums, just like what we did in this simulation, or averages of an independent random variable will approximate a normal distribution. Now, why is this so? If you think about our simulation, and especially if you really did flip the coin yourself by hand, you can consider that there are multiple sources of variation in the outcome of each flip. That is, there are multiple reasons why a particular flip might come up heads. You know, how forceful your thumb was, some sort of passing movement in the air above your hand, etc., etc. So there are multiple different reasons why a particular coin flip would come up heads, and to use this as a simulation for a real diagnosis, we can imagine that there are multiple sources of variation for why each individual participant in your sample might have the particular diagnosis. Now, in the case of diagnosis, some of those sources of variation are going to be systematic, particularly whether or not that person really does have the disorder, whereas other sources of variation are going to be unsystematic. There could be kind of mistakes that the interviewer made when conducting that particular interview to make the diagnosis. There could be misunderstandings or confusion on the part of the client or participant in terms of how he or she responded to the questions. It could be just mistakes made when entering data into the computer, etc. Those things, really having the disorder and all this other unsystematic sources of variation, will factor into whether a particular person is comes up heads, so to speak, whether we give them the diagnostic label of having the particular disorder. Now, the central limit theorem assumes that these unsystematic sources of variation are independent and are randomly and evenly distributed across our data set. And that has a really important consequence. It means that these influences, these unsystematic sources of variation, will sum or average to zero across our data set. In contrast, the systematic sources of variation aren't randomly distributed. So they sum to the, quote, right value, that is, an estimate of the real population level of, in this case, the disorder. Now there's an interesting point here. In our simulation, the outcome variable is dichotomous. Again, for any one participant, the diagnosis is either present or it's not. So dichotomous variable. And if we made a distribution of values for a sample, that is one set of 4 flips or 8 flips or whatever, we wouldn't expect that distribution to have a regular shape, like a normal shape. So for instance, we could, in one run of 4 flips, just count the number of times heads comes up, and it came up for participant 1, it didn't for participant 2, it did for 3 and 4. That shape of that funny looking distribution there clearly isn't symmetrical, it doesn't look like a bell curve, it's not a normal distribution. Likewise, we could create a test statistic like the sum, and we could say that for that sample the count of heads was 3 and the count of tails was 1. And again, that distribution there doesn't look like a symmetrical curve, it's not a normal curve or anything like that. However, if we create that statistic, for instance in this case, the total score of heads, or total number of heads, or total prevalence of the diagnosis in our sample, and if we compute that same statistic repeatedly, especially from large samples over time, and create a sampling distribution of those values, that shape will look normal. So just to remind you of what it looks like, here's our sampling distribution for sample size n equals 4, which is far too small to be considered a good sample size. But even that sample size kind of has a symmetrical shape, and it sort of looks at least like it's beginning to be a normal curve. Now, why am I telling you this? I think this is kind of an important point. When researchers gather a sample of data, they often check to see whether that data has a normal distribution. And sometimes they really worry if it doesn't have a normal distribution. This only makes sense to the extent that you expect the sample data to be normal in shape. And there may be situations in which you do. So for instance, if you gathered a fairly large sample and you measured a variable which you think is kind of normally distributed, like say the level of a personality trait, you might well expect to see a normal distribution in your sample. And if you didn't see one, you might think, well, that's odd, maybe there was a mistake, maybe something went wrong with our recruitment, and so on. This idea of looking at a sample distribution and seeing whether or not it's normal also makes sense to the extent that you're looking for odd values or shapes. If you're looking to see if you have a problem with skew that is unexpected, or if there are odd outlying values which distort the shape of the distribution. The important point here is that the shape of the sample distribution is important, and looking at it can help us identify odd values like outliers, or it can help us identify potential bias in our estimator. Like if our distribution is just really skewed, then maybe the sample mean isn't going to be a very robust estimator of the population mean. But as important as the sample distribution is, the sampling distribution is in many ways more important. At least it's more important for a lot of the data analysis that we'll do. And that's stuff I'll get to a little bit in this lecture and much more so in the coming lectures. So it's important that our sampling distribution have a regular, normal, in most cases, shape. And it's also good to know that that sampling distribution will have a normal shape even if the sample distributions are not normal, provided that the sample size for those samples is large, and provided we make some assumptions about the nature of our sampling procedures and the nature of our sources of error, which I won't get into right now. So the really important point here is that large samples are better than small ones. And there are all sorts of reasons why having a large sample of data is better than having a small sample of data. But the one I'm driving at right now is that sampling distributions that are from large samples are more closely resemblant to a normal distribution and more precisely estimate parameters, for instance, the prevalence of a disorder or the average level of some variable, or so on and so on. And to look at it one last time, here's another simulation. This is just a simulation of runs of 500 samples drawn from a population where the population mean is 4.5. And so you can see on the left side, we've got sample size n equals 5 that has been drawn 500 times from the population. Each time the sample mean was computed and a sampling distribution was made. The mean of that sampling distribution is about 4.64. So it's a little bit off from the population mean. In contrast, if you look on the right side, you can see sample size n equals 50, drawn 500 times from the population, and the sampling distribution has been sort of graphed there. The mean of that sampling distribution is 4.5. It's right dead on the population mean. So again, larger samples, sampling distribution is going to be more regular in shape, more normal in shape, and the estimates of parameters like means and totals or whatever are going to be much more precise. Thinking about this reminds me of a famous quote from one of Jacob Cohen's many papers. Jacob Cohen was a famous psychologist and statistician who really did a lot to help us all learn about how to use multiple regression and correlation analysis as a kind of a framework for doing a lot of our statistics. And in one of his papers, he's kind of reflecting on the things that he's learned over the years, and he says, one thing I learned over a long period of time is that less is more, except for sample size. And by the way, the less is more he's referring to is the idea of having simple models, models which are relatively parsimonious. But he says, it's good to be simple, it's good to be small, except in sample size, which should be big. And I couldn't agree more. So hopefully this simulation made sense to you. Hopefully you can remember this important reason for having large sample sizes. But to move on a little bit, we can ask, why is all of this important? Well, it's important because if we understand the sampling distribution of a statistic that we have computed, then we can know the probability of that statistic over a long run of samples. Here it's maybe useful to reflect on the idea or the fact that sampling distributions are sometimes called probability distributions in some stats textbooks, and the reason for that is that they describe the probability in the sense of occurrence in frequency over a long run of samples of different values. So you can say, how frequently is it the case that we get a total score of 4 on 4 flips of a coin, or an average of 68.23 when we draw samples from a population where the population mean is 60, and so on. We can think about the probability that a particular set of observations or sample would occur in a given population. And thinking about this, of course, reminds me of that quote from Carl Pearson, which I've used before. I've just highlighted here probability distributions. This is Salzburg writing, "Before Pearson, the things that science dealt with were real and palpable, in a sense, the sample. Pearson proposed that the observable phenomenon were only random reflections. What was real was the probability distribution. The probability distribution of all the values that we would get for things like totals or means or whatever, if we could repeatedly for a very, 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 very large number of times sample a population." And this is the basis of hypothesis testing, at least the type of hypothesis testing that we're really going to emphasize in this class, and that is most commonly used in psychology and in the behavioral sciences. So to kind of bring us away from coin flips and sort of disease prevalence, let's go back to that example of the College Counseling Center. And the basic idea of hypothesis testing in this context is we want to know the probability of our sample statistic, like a sample mean, for instance, in a given sampling distribution. And if that probability is relatively low, falls below our threshold of p less than 0.05, we experience the joy of statistical significance. So we've got our one sample of people that we've drawn from our population, and we've got a sample mean for them, and we want to ask the question, is this sample mean significantly different from 60, our hypothetical value? Now, if you think back to other stats classes that you've taken, you probably remember that the z-test is an appropriate test to do to evaluate this question or to test this hypothesis. So in our example, we could just plug in the numbers for our observed sample mean, subtracting from it our hypothetical population mean, and dividing by the standard error for the mean, which we can compute based on the standard deviation of our sample and the sample size, again, because our sample size is pretty big. We've got 60 people overall. And the z-test is just allowing us to, again, ask, is this a statistically significant difference? Or put another way, would it be rare? Would it occur, for instance, less than 5% of the time in a sampling distribution that we draw a sample size of 68.2 if the population mean, if the center of that sampling distribution was 60? So if you're working in Excel, you can go ahead pretty easily and compute some of the values you need. You already have, probably from previous work, the mean and the standard deviation. You can compute the sample size, or you can just look to see that the sample size is 60, and you can compute the standard error by dividing the standard deviation of the sample by the square root of the sample size, as I've done here. Then you can go ahead and calculate the z-statistic by using the formula from a couple slides back, if you want to. And then getting the probability value associated with that z-statistic involves using a function called norm.s.dist in Excel. And this may look a little bit fussy, but the important point to notice here is what we're saying to Excel, or what we're asking Excel is, hey, here's this particular value, the value of our z-statistic. Can you go ahead and see how commonly it occurs in a normal distribution? So how commonly would this value show up? And by the way, true, the argument true, gives us the cumulative probability, the area to the left of our test statistic. since we want to know the area to the right of our test statistic because we're doing a one-tailed test, I'll talk about one-tailed test and two-tailed test in a future lecture, we just subtract that value from 1. And that gives us our whole argument here, 1 minus norm.s.dist, the value, comma, true, and close up all the parentheses. Now this is the probability, the p-value of our test statistic or any value larger than it in a normal sampling distribution. And if that value is low, like less than our commonly used criterion of 0.05, 5% of the time in a long run of statistics, then we say, aha, this difference is statistically significant. By the way, if you like to use Excel but you feel a little bit daunted by all the steps to do a humble z-test, thankfully Excel has a z-test function for you. It's conveniently called z.test, and it gives us the same p-value. You can actually see that if you do it in a separate cell. The function is z.test, and then you give all the values that you're trying to test in your sample, and you give it the hypothesized value in the population, which you can see here is 60. And you get the same probability value, the same p-value as a result. So again, the function z.test can take an argument for the hypothesized mean value in the population. It can actually also take an argument for the population standard deviation, but in this case we're using a sampling distribution of the mean, and so we can skip that argument and just let the function automatically substitute in the standard error, which is computed from the sample standard deviation. Okay, so hopefully what you just saw in those last few slides is a bit of a quick review of the z-test and maybe a connection between the z-test, kind of how it works, and this idea of probability distributions or sampling distributions for a statistic. If that still seems a little bit unclear to you or how that works, don't worry, because in the next lecture I'll talk some more about hypothesis testing, particularly hypothesis testing from the perspective of model comparisons, where we're comparing one model of the data to another model of the data and trying to decide which one we think fits the data better. And this kind of leads me more broadly to this discussion of making statistical decisions, which I'll start in that lecture and continue in future lectures. Okay, so I told you this would be a long one. It's actually not much longer than some of my other lectures, but if you made it this far, thank you very much for all your attention. Take a break, take a rest, make yourself a cup of tea or a cup of coffee or something, and I will be back very soon with my next lecture, and hopefully you will too, to watch it. In the meantime, if you have questions and you're enrolled in my class, by all means ask me. If you have questions but aren't enrolled in my class, leave them in the comments area on YouTube. I try to be vigilant, and if I see a comment or a question, I try to respond to it. So thanks so much, take care, take a rest, and hopefully you've learned something. I know I have. Bye-bye.